Okay, then next up we have the second talk. So it's given by Matteo Calosci, who's going to talk about displayed universal algebra in UniMath. Yes.
Thank you for the introduction and for the organizer for organizing this event. I'm going to talk about a joint work with Gianluca Amato, Marco Maggesi, and Cosimo Perini-Brogi. And we'll tell you about our formalization progress about the subject of universal algebra in the UniMath proof assistant. And I will focus on our newest addition of our formalization, displayed algebras. So the goal of our formalization project is to present to formalize a pre-categorical presentation of universal algebra. So our notion of algebra will be that of some types with added a certain structures. Another goal is that we want to have available constructions in a sense that I will explain later. Our code is open source in our GitHub repository, and as of today is merged also in the official UniMath distribution. Okay, we work with Univalent Foundation, so we have dependent types and the usual dependent function, dependent pairs, coproduct, empty type, unit type, and natural number, and propositional equality as the inductive type generated by reflexivity. Also, we have the univalence axiom, which allows us to identify isomorphism in the case of our algebras, and the propositional equality, which seems convenient for this subject. For the precise implementation of this foundation, we chose UniMath, which offers a minimalistic implementation of univalent mathematics. So I have to note that general inductive types are avoided to keep the system sound from a semantic perspective. And also we chose UniMath because of its vast formalized mathematical results. So we have many ready-made structure which we can use for apply our result or target for example and application. There is also a lot of developed categorical notions on UniMath, which allows us to state the initiality, some result about our category of algebras. And also there is some development about a categorical presentation of universal algebra, which we hope to develop some connection in the future. Okay, before going to displayed algebra, I want to briefly list what's already in the formalization. We work with multi-sorted signature, so that a signature to us is just a triple made up of a decidable set of sorts symbols, a set of function symbols, and an arity function assigning to each function symbols a list of input sorts and a single output sorts. So then an algebra is just a collection of types indexed by sorts. I will refer to these types as supports. And to any function symbols, an actual function from the product of the supports of the arity to the supports of the output sorts of the considered function symbols. We have some basic construction of algebras, such as the unit algebra, which is the terminal one in which any support is the unit type. And more interesting, we have construction for the initial one, which is the one of the ground term algebra, the algebra generated by the syntax. We have an interesting construction for this algebra. We construct ground term using list stacks and maybe monad. The main idea here is that we take function symbols and we make these act on stacks of sorts symbols by checking if the top of the stack is exactly made up of the input symbol for the arity of the function symbol. And if this is the case, we replace it with the output symbols. If this is not the case, the stack is really a maybe monad, so we have a status of error. So if instead of a single function symbol, we have a list of them, we can iterate this construction. And the idea is that we encode the term using a prefix notation as a list of function symbols. Obviously, not all list of function symbols correctly encode a term. The list of function symbols which correctly encode a terms are those which, when we make them act on the empty stack of sorts, we get in return just a single source, which will be the source of the term. And if instead we get at any point an error status, we just propagate it. So the predicate which tell us if a list of function symbols is a term is a proposition in the UniMath sense, and or in the UF sense. And from this construction, we derive introduction, elimination, and propositional computation for terms, which we in turn use to give our constructor of term algebra, and more generally, the free algebra generated by a collection of variables. Another result that we have in the single sorted case is that this construction can be encoded as an homotopy W type, so that terms have the expected tree-like structure. We have the notion of homomorphism between two algebra, which is just a collection of functions, again indexed by sorts, and they shall make the obviously diagram commute. So if I have a vector of terms for which I can apply a function, if I first apply to each of them the homomorphism maps and then the interpretation in the target algebra, the output should be propositional the same of applying first to each of one the interpretation in the source algebra and then the homomorphism map to the output. This notion of homomorphism behaves well with identities and composition, and in fact it gives us a pre-algebra. If we furthermore assume the support types of our algebra to be sets, this is indeed a category in the UniMath sense. This means the home type are sets. And furthermore, under the same hypothesis, this category is univalent, so that isomorphism corresponds to propositional equality as expected. We also have just a basis for talking about equation. An equation is just a pair of terms of the same sorts, possibly with variables, and an equational specification is just a collection of equations. An equational algebra is then just an algebra in which all the equational specifications are valid propositionally. We have also some examples. I will not go in details now for time reasons, but the main point is that if we take an algebraic structure already defined in UniMath and we present it as an algebra with our formalism, we don't lose judgmental equalities holding in the starting structures. Okay, now I'll focus on the latest addition to this formalism, which are displayed algebras. Okay, the idea of displayed algebra is that displayed algebra is just some data on top of a base algebra B over a given signature sigma. So precisely this data is that of a collection of types, which we call fiber types, indexed over terms of the base algebra. And then a family of over-operation, just a name, a family of function, which we call over-operation, indexed over any operation name of the signature, and also indexed over any vector v of suitable term for application to a function of the base algebra. So to make an example, I have this drawing. The black ellipses is the base algebra B. It could be made of more sorts. And let's say we have a function symbol nm, and so we have an operation in the B. We have the interpretation of nm as a function of B, and let's say this maps the vector of the first two dots, which represent terms, to a third one on your right, and then our over operation Okay, then over any of these dots, there are ellipses representing the fiber types corresponding to such term, and the over operation then should map vector of terms taken from the first two fiber types to the third one over the output. Okay, the idea of displayed algebra is not original. It's already implemented in UniMath for categories. And also there is something in the literature also for the case of universal algebra. And the main idea, I think also in the category case, is that displayed algebra do not bring any more information than just a morphism targeting the base algebra, or in the categorical word of a functor targeting the base category. And so the reason why we still think offering this formalism is interesting is just the same of the categorical setting, is that we can this way give modular construction in a, we think, more natural way. Okay, the main result we have formalized is just this, that displayed algebra are equivalent to morphism targeting the base, and I will go a bit more in detail about this. So first of all, from the data of a displayed algebra, we can construct an algebra of the same signature of the base, and this is the total algebra. And here the support types are just the sigma types, in which the second component are the fiber types, and the operation are just sigma type, in which the first component you have the function as interpreted by the base, and the second component you have the over operation, which I talked about before. There is the projection on the first component, which is actually an homomorphism. We call it the forgetful homomorphism, which goes from this total algebra to the base algebra. If we instead take any homomorphism targeting an algebra B, we can construct the displayed algebra of its fibers, in which the fiber types are just the fiber under the homomorphism of the specific index terms. And the over operation is given essentially by the morphism, and the fact that the source and target of this morphism are the one expected comes from the fact that H is an homomorphism. So these two constructions, the forgetful homomorphism and the fiber display and the displayed algebra of the fiber, are inverse to each other, and we can use them to build an Vygotsky equivalence between the type of morphism targeting B and the type of displayed algebra over B. We have some examples, some study case for this, and first of all, the notion of subalgebras. There are, we think, two natural ways of introducing subalgebra. For example, as an embedding targeting the algebra, targeting B. An embedding is just an homomorphism which is injective on any support. Or more classically, we can think of a subalgebra as a subuniverse of B, and this will be just a collection of subtype, one for each support, and this should be closed under the operation. So if I take a vector of terms, each of them in one of these subtypes, and I apply an operation of V, then I want to get a term still in one of these subtypes. And since subtypes are just predicate over a type, which are propositions on each argument, this notion is almost judgmentally the same of that of a displayed algebra, in which all the fiber are proposition. And so the equivalence of before specialize in this case, and we have formalized that the types of embedding targeting B is the same as is equivalent to the type of subuniverse of B. For both this result and the previous one, we have assumed the base algebra to be set supported, I conjecture it's not necessary, but you have to do much more unfolding of construction to prove the appropriate path algebra results. So this is not yet done. We have some more examples, which we aim to develop more in the future. About examples of algebra presented as displayed algebra, obviously product and pullback, we think we can try to implement this one. Or for product, we already have an implementation, we want to prove its equivalent. And also, we think really nice examples in which this displayed structure really comes natural will be that of the implementation of the semi-direct product of groups. For the development of the theory, we think we will use the notion of displayed algebra for stating the homomorphism theorems. And also, maybe it could be interesting to see the relation with quotient, since a quotient would be the base type for displayed algebra. Also, we want to investigate the results about composition of displayed construction. So we'll conclude with just some word on other future development we have in mind for the library. We aim to construct the initial algebra of terms modulo equational congruence, the Birkhoff's variety theorem, and also the result with homotopy W types. We want to try to generalize it to the multi-sorted case. There are some technicalities. Many of the difficulties in this implementation comes from the fact that the main engine, let's say, under the hoods is this notion of heterogeneous vector. If I have a vector of types, I want to consider the product type of these vectors. But these quickly create many ways to state equivalent types, and this doesn't scale well with added parameters. So maybe it could be interesting to see if their implementation can be done differently or better. And also the think about the link with the categorical presentation of universal algebra. Thank you.
Questions?
In one of the last slides, you used this word set supported. What does that mean?
I mean the types which are the support of our algebra are sets in the Univalent foundation sense, so that equality.
Okay, thanks.
The carriers.
The carriers, yes.
Other questions? Yes, Torsten.
Hello, thank you. I just wondered, why don't you use inductive definitions? I mean, this makes it very hard to read new constructions.
Okay, I think in UniMath they are avoided for semantic reason, for keep the system sound. And just as I don't have a really good.
Because you use UniMath, okay. Yeah.
Other questions? I have a question. There is some work by William de Mayo and I think a few other people about universal algebra and Agda. I think they have Birkhoff's variety theorem as like one of the key things. Can you say a bit about how it relates?
I am not aware of the.
Okay, that's another thing. I think they use setoids actually, so there should be some differences. But, okay. Other questions? No? Then let's thank the speaker.
Thank you.